understand the nature of fundamental interactions by studying properties of elementary particles. He is one of the first Indian bronze medalists in the International Mathematics Olympiad. He has received the Institute, the Silver Medal from IIT Bombay and the John Bell Scholarship. He was the leader of the Max Planck India Partner Group in the neutrino physics at astrophysics for 5 years. He has been elected Fellow of the Indian Academy of Sciences and the Indian National Science Academy. He has won the Swarna Jayanti Fellowship from the Department of Science and Technology, and he is the recipient of the Shanti Swarup Bhatnagar Award. Now I hand over the session to our convener.
So thanks to the organizers for having this special session on INO, and I hope that in the next one and a half hours you will get a good idea of what this mega project is all about, its science, technology involved, and opportunities for industry as well as students. So before we proceed further, I would like to introduce my co-convener, Professor Dinesh Rangappa. He is working at the Vishwesvaraya Technological University in Karnataka. His research interests are nanostructured materials, supercapacitors, solar cells, and nanostructured materials for biological applications. He has delivered several invited and keynote talks at various institutes and conferences at India and abroad. He is a recipient of JSPH Fellowship Award and is the first Indian to get the Yoshida Scholarship from Japan under the Asia 100 program. He has published more than 50 papers in peer-reviewed journals. So I would like to welcome him, and he will first conduct the session. Since it would be easier for both of us to see the slides by sitting in front, I think we will see sitting that in the front. So, good. So let me, before we call our first speaker, let me just give a short introduction to a short trailer, so to say, of what we are going to see. Yeah, you can see. So you might know that one of the first detections of the atmospheric neutrinos happened in India, not very far from here. It happened in the Kolar gold mines in Karnataka in 1965, so which is almost about 50 years ago. Jumping ahead, some of you may have attended the talk of Professor Kajita on the first day, who won the Nobel Prize for discovering neutrino oscillations, which showed that neutrinos have mass. In fact, the work of Professor Kajita was based on the observation of atmospheric neutrinos, which shows you why they are important even today. And coming soon to a mountain near you is going to be the India-based Neutrino Observatory. The picture that you see here is the same as the picture that you might have seen on the proceedings front page. It shows that neutrino research indeed forms a front page of Indian science. This is a detector that you are going to be placed inside, and you will learn more about all these things in the talks that are given by our 4 distinguished speakers. The first will be Professor Uma Shankar. He will introduce you to the field of neutrinos and oscillations at the India-based Neutrino Observatory. Then we'll have Professor Prafulla Behera. I'm sorry for the typo in the name. It's not Behere but Behera from IIT Madras. He will introduce you to the ICAL detector. Next, we'll have Professor Indumati, who will tell about constructing of this underground science mega project in India and what are the things that we should be taking into account, because this is perhaps the first time that we are building such a big thing in India. And the final talk will be by Dr. B. Satyanarayan from TIFR, and he will tell us about the industry interface of IIT and opportunities that you are going to have for students. So with this, we'll start with our talks. I will like to invite my co-convener to introduce the first speaker. 1 minute. So just one suggestion for people. It turns out that this projector is much better than this one. So if you move on this side of the tent, then you would perhaps have be able to see the slides much better. Thank you. In between we get notification. Okay.
A very good morning to all ladies and gentlemen. First of all, I would like to invite Professor S. Umashankar on dais. So Professor Umashankar is working in a physics department IIT Bombay since 1994. He has been working in the field of neutrino physics for over 20 years. He has graduated from IIT Madras in 1982 and he did his PhD at the University of Pennsylvania in 1988. He was a visiting fellow at the TFIR, a postdoctoral fellow at the University of California, Riverside, and a fellow at the Institute of Mathematical Science, Chennai. So now Professor S. Umashankar will take over the session.
Slide change. Okay. I thank the organizers and the conveners of this session for giving me this opportunity to give this talk. And so I will first give a general introduction to this idea of neutrino oscillations, and then I will talk about neutrino oscillations at INO in particular. In one question which people, scientists and philosophers have thought about probably from past 2,000 or 3,000 years is what is matter made of, and of course there were various speculations, but a substantial and quantitative picture started emerging, I would say, in the last 300 years. First, people realized that if you go to the smallest part of any given matter, you will encounter a molecule, but later advances in chemistry showed that all molecules are made up of combination of a rather limited set of atoms, that is only about 92 or so. But about 100 years ago, there was a even more drastic simplification of this picture, which said that all matter is made up only of three fundamental particles: positively charged proton, negatively charged electron, and a neutral particle with no charge, which is neutron. And everything we see in the universe is made up of these three particles in various different combinations. However, there is one aspect which is troubling. In beta decay, that is a neutron decaying into a proton, the energy is not conserved. If we apply conservation of energy, energy of electron should be mass of neutron minus mass of proton. But when you do the experiment and measure the energy of the electron, you get that continuous distribution varying from 0 to a maximum value of neutron mass minus proton mass. So does it mean that we give up on energy conservation? Some people actually were willing to do so, but Pauli is a great believer in energy conservation, and he said, I will use this, what he called a desperate remedy of proposing that there is actually a third particle also which is produced, and this third particle is taking away the missing energy. And that is the proposal of neutrino. That is when people first started talking about neutrinos, and to account for the data, this third particle, it should have zero charge so that conservation of electric charge holds, and also conservation of energy implies that the mass of this third particle should be much smaller than electron mass, which is already the lightest known particle. And a fellow physicist called Fermi named this particle neutrino, meaning Fermi is Italian, and so in Italian neutrino means little neutral one, to distinguish it from neutron, which is the massive neutral particle. And this neutrino is the first of the various exotic particles which people have discovered over the last 80 years or so, and I am sure all of you have heard of this great excitement which occurred about 5 years ago when the Higgs boson was discovered. So Higgs boson is, as of now, the last entry in this list of exotic particles, but we hope that there are many more entries to come. This same Fermi, he constructed a theory of beta decay based on Pauli's proposal, and this theory agreed with the data so well that people just accepted that there is a neutrino, even though nobody ever saw a neutrino. And in fact, people made an estimate about the chance of actually observing a neutrino in the lab and concluded that it's not possible at all. The reason is, you take a neutrino, let's say, of energy 1 MeV and an electron of energy 1 MeV, and both of them enter a detector, and the probability that neutrino will interact with the detector is 10 power 18 times smaller than the probability that electron will interact with your detector. So if you say that electron will interact in a microsecond, then the probability you have to wait some 10 power 12 seconds for the neutrino to interact. That is like a million years. So chance of observing a neutrino interaction seems very small. I mean, practically undetectable. However, in fact, this is a famous cartoon which illustrates the situation, that just because you proposed a particle but say that it's undetectable doesn't mean that it exists. But mind you, in the case of neutrinos, we have very strong reason to believe that it exists, because the Fermi theory, which is based on neutrinos, explains data extremely well. But all this was before World War II, and after World War II, one had nuclear reactors, and nuclear reactors were putting out something like 10 power 12 to 10 power 14 neutrinos per second. So if you wait for a couple of years, then there is a chance that you can actually observe neutrino interactions. So based on that hope, 2 experiments were conducted. One looked for conversion of a proton into neutron, and the other looked for conversion of neutron into proton. induced by neutrino. The proton to neutron conversion experiment, it saw a signal. They could see the neutrons being produced in their detector, and in fact the person who conducted the experiment was awarded Nobel Prize in 95. But the other experiment, neutron to proton conversion, did not see a signal. There were no argon atoms in the detector. And of course we understand this by saying that it is antineutrinos which convert protons to neutrons, and neutrinos convert neutrons to protons, and reactors produce antineutrinos. That is why the first experiment saw a signal and the second experiment did not see a signal. Obviously, the person who did the second experiment, he was very upset, and this is this gentleman called Ray Davis, and he started looking for a source of neutrinos so that he can also see a signal. And the source he found is the sun. There are nuclear reactions, nuclear fusion taking place in the sun, and in the process of nuclear fusion, enormous number of neutrinos are being emitted. In fact, even though the sun is so far away, something like 100 trillion neutrinos are passing through each of us every second. So there are enough neutrinos to detect, and Davis indeed succeeded in detecting these solar neutrinos. And here I want you to sort of think of the achievement. He had a detector which is like 1,000 tons, which contained something like 10 power 36 atoms. Out of 10 power 36 atoms, he managed to pull out the 10 argon atoms from the detector. People talk about searching for a needle in haystack, but this is like needle in a billion haystacks. However, there is a problem. Problem is that the value measured by Davis is only 1/3 of what is expected, because we have a reasonably good understanding of how the sun is producing energy. Then question is, why is that? Is something happening to the neutrinos as they are coming from sun to earth? And this is the first hint we have that neutrinos are not just showpieces just there to conserve energy. They actually have much more interesting properties. Well, that is one of the surprises we had, but nature had many more surprises, and in particular people studying cosmic rays in the 1930s, they found some very puzzling features, and they finally explained those features by saying that there is another exotic particle called a muon. This muon is a charged particle, and it is some kind of heavier cousin of electron. Electron has unit charge and it has mass of something called half an MeV, whereas muon also has unit charge and it has a mass of about 100 MeV. And here I should mention that Dr. Homi Bhabha, who set up the Indian atomic program, he played a key role in figuring out this puzzle, and in fact I believe he was considered for a Nobel Prize, but for some reason he was not awarded one. And scientists, after discovering the muon, started studying its properties in a systematic manner and found some more puzzling features. And in order to explain those puzzling features, they had to propose that there is actually another neutrino which is different from the neutrino that was proposed by Pauli. And so they started naming things systematically. Pauli's neutrino is called electron neutrino, and this neutrino which is coming in muon decay is called muon neutrino, and the proposal was made sometime in 1950 or so, and 10 years later in an experiment in the US, this muon neutrino was explicitly seen, and this experiment also was awarded a Nobel Prize in 1988. Now let us talk about this muon neutrinos. The experiment done in the US produced muon neutrinos quote artificially. They produced them in a lab, but people doing the Kolar Goldfield experiment, they realized that these muon neutrinos are also produced naturally in the atmosphere, because you have cosmic rays coming and hitting an atom in the atmosphere, and that interaction, there are large number of steps, but eventually that interaction produces this muon neutrino, and you can detect those muon neutrinos in the Kolar experiment. And as Amol already mentioned, in 1965 the Kolar Goldfield experiment detected these muon neutrinos in atmosphere for the first time. Now let us come to this business of neutrino oscillations. Soon after the discovery, just months after the discovery of second neutrino, 3 Japanese physicists, they proposed this, you can say, really wild idea in which an electron neutrino can spontaneously turn into a muon neutrino. In all the previous transformations we talked about, there is a decay or an interaction. Here there is no such thing. I have an electron neutrino coming like this, and spontaneously it becomes a muon neutrino. So this is something completely different, and but it's a possibility, and that is what these Japanese physicists proposed. And for this oscillation to occur, 2 things should happen. The 2 neutrinos should mix in some way. I mean, one can define this mixing in a mathematically precise way, but I don't have time to do that now. And another important thing is that the 2 neutrinos should be massive, very small mass, mind you, maybe million times smaller than electron mass, but non-zero mass, and also unequal masses. That's the requirement. And the probability of oscillation depends on the 4 quantities that I listed there. And after this proposal, people started speculating whether the deficit of solar neutrinos that I mentioned earlier, whether it is due to neutrino oscillations. So this is the first hint we have of neutrino oscillations. Now let us talk about a different problem, which is called atmospheric neutrino problem, and that begins with this famous statement by Richard Feynman. I am sure all of you have heard of Feynman. His lectures are very famous. Fermi once made a statement that yesterday's discovery is today's calibration, to which Feynman added, well, yesterday's discovery will become tomorrow's nuisance. But here this atmospheric neutrino problem is a case where what is meant to be nuisance actually gave rise to a discovery, and that discovery came through this means. Professor Kajita talked about it and he got a Nobel Prize for it. There are neutrinos coming from all around the earth. Those coming from above are travel few kilometers, those traveling from below travel thousands of kilometers, and those coming from above do not oscillate, but those going from below, they oscillate. So there is a atmospheric neutrino deficit, and this is the data for which Professor Kajita got the Nobel Prize, and this is our present knowledge of neutrinos. There is a larger mass square difference and smaller mass square difference, and what we try to do in INO is to study that larger mass square difference in detail, and why exactly do we need to construct INO? It is the only atmospheric neutrino detector with a magnetic field, and this magnetic field enables us to study matter and antimatter separately, and that provides a much better detail of the whole neutrino physics and atmospheric neutrino problem compared to all the other detectors. So, and over the past 15 years, there is a large enthusiastic group of young researchers and PhD students who are working on INO, and we all hope that this project will start soon. Thank you. We'll have questions later. Okay.
So we will have questions later at the end of this session. So second speaker, Dr. Prafulla Kumar Behra. Dr. Behra is working as an associate professor at IIT Madras since 2011. He works in the area of experimental high energy physics since 1998. He is a leading detector R&D efforts for INO experiment. His experiments during his PhD and postdoctoral period measured CP violation that led to Nobel Prize in Physics in 2007. He worked in ATLAS experiment as a scientist at University of Iowa and one of the co-authors for the journal paper that announced discovery of Higgs boson that led to Nobel Prize in Physics in 2013. He has more than 750 peer-reviewed journals publication. So I would like to welcome Dr. Behra for his talk.
Okay. Thank you for brief introduction, and let me go to the next topic, which how we address this physics issue, and for that we need detector, and my talk will be focusing on the detector, how we are going to build and what are the difficulties, what we are going to get out of this detector. So this is my outline. First is I will talk about the neutrino detection. This is very important, and then just to touch base on particle detectors, then see what our detector is called iron calorimeter, where we stand, how we are going to build this, and I will conclude my presentation. In dedicated neutrino experiment, it is very difficult to detect neutrino, as mentioned by previous speaker, because it interacts very weakly with matter. So if you want to detect neutrino, you have to have large amount of interacting material which is called mass. For ICAL, we have iron as the catalyst. So with iron, we can detect neutrino indirectly. I will talk about how. In accelerator experiment, like you have heard about Higgs boson, all other experiment, why don't they do this measurement, and why do we need a dedicated facility like INO? Because If you go to electron-positron collider, which led to Nobel Prize in CP violation, they also produce neutrino, but they cannot, because in their experiment, all the three momentum of the particle has to conserve. If you go to proton-proton collider, which discovered Higgs boson, they also produce neutrino, but they cannot detect neutrino. So there is a limitation that if you want to study neutrino properties, you have to have dedicated experiment like INO. Why do we need the detector? Detectors allow us to detect particles. Experimentally study their behavior, this particle's behavior, and new particles are found by direct or indirect, or through their decay you can detect the new particles, or you can study the properties of known particles like neutrino. Theorists predict the properties, experimentalists design the particle detectors and build the detector. What do we do? Measure using this detector. What exactly we do with this detector? We want to know the location, the path where the particle has gone is called spatial location in ICAL. The trajectory, if you have, that's not enough. To do the measurement, you need the magnetic field which will help you to measure the momentum and the charge of the particle. You can also measure the production point where the particle has been produced and when it decays. That will allow you to measure the lifetime of the particle. You can also measure the energy. This is in ICAL we do want to measure the energy. There we have the relation momentum plus energy gives you mass. Okay. This is just one slide to tell you that all the collider experiment, they have multiple number of, means very different detector together make one detector. If I talk about Atlas or CMS, you have many detectors. You have a tracking detector which measures the trajectory. You have an electromagnetic calorimeter, measures the energy of photons, electrons. You have hadron calorimeter which measures the energy of hadron, and you have muon detector which measures the muon. You see, you need 4 different detectors to do the experiment. If you look at the left hand side, it shows you photons, electron, muon, pion, everything you detect, but nothing is about neutrino. So the question is, this detection of neutrino is a challenge actually, and you have to be very patient to do this kind of experiment. How do I going to measure this detector, build the detector and do the measurement? The first thing is direct detection of neutrino is impossible as mentioned by our previous speaker because it's a weak interacting particle. Okay. So because it's a cross section, the interaction cross section is very small. Just for example, if you think a few MeV neutrino you want to have interaction, one you need like 10 light years of thickness of steel plate. This is what you think. So this is a challenge actually, and once the theorist, which is Wolfgang Paul, made a statement, I have done something very bad today when he proposed this by proposing a particle that cannot be detected. It is something no theorist should do ever. But now we are detecting neutrinos. The things have improved. How ICAL is going to detect neutrino? Neutrinos are detected through their interaction with nucleons. In case of ICAL, with the iron provides this nucleons, resulting the new particles, which is muon and pion. Basically, when neutrino comes, interact with the nucleons, you get muon and pion. That tells you that neutrino has interacted. Through the detection of muon and pion, you can do everything about the neutrino which has produced this. This is like indirect way. So in our case, it is important to measure muon and pion. So ICAL detects muon and pions. Finally, we get the energy and direction. That will give us the neutrinos energy. That is used for all the physical measurement which the previous speaker talked about. So in case of detector, what we do basically, we measure the momentum and energy direction, put into the formula given by theorist and do the final product. Okay. What are the challenges for ICAL? Is it so easy or is it difficult? We'll see. The special thing about ICAL, as mentioned by previous speaker, that this has the capability to differentiate between neutrino and antineutrino by detecting positive and negative muons. It doesn't say muon, it will tell you whether it is a positive muon or negative muon. That will tell you whether it was produced by neutrino or antineutrino. This picture has been shown many times. So this is 50 kiloton which is proposed for the ICAL detector. We don't build 50 kiloton at a time. We have to see the granular way. What is the smallest building block of this 50 kiloton detector? The smallest building block is called this RPC, and this RPC is 2 meter by 2 meter glass. So smallest building block is 2 meter by 2 meter glass RPC, and we use 30,000 of this to make this gigantic detector. Then what I mentioned actually, we also want to measure the muon and anti-muon or mu plus and mu minus. For that, we have to magnetize this big gigantic detector, and it has never been done in the world to make the so big electromagnet. So this is a challenge for engineering purpose also. It's never been done in the world, and we are going to do the first. What do you see in the detector? Once you see the detector, this is the detector volume. Once neutrino comes, it interacts, and it gives you two types of hits. The first one is muon, which gives you a trajectory where you can measure the momentum. But in case of red color one, is called hadron, is pion. It's a strong interacting particle. It gives you a bunch of hits because it's a strong interacting particle. It loses all the energy quickly. So challenge is to separate this hadron and muon, make sure that you separate them, otherwise you mix, then you will not get the proper measurement. That's a challenge for us. If you remember my previous slide, all the experiment uses the particular detector for measuring particular particle. In case of ICAL, we are using one detector to detect muon and hadron. This is a challenge. How do we do that? So we don't make this 50 kiloton ICAL in few years also. First you start with a very small detector in your lab, which is called R&D, which has started 15 years back before we go to the big detector. I will go through this small piece which basically gives you a proof of principle how you go for 2 meter by 2 meter RPC and make 30,000. First you can be in the lab, you don't need to do 2 meter by 2 meter, you can give the 1 feet by 1 feet glass and make this gap. So glass is bad conductor. So what you do actually, you make a coating to make it conductor. So you make two glass plate and put together with 2 mm gap. And if you see this gas gap is, the gap is there because we need to provide the gas which will use for ionization when the particle pass through the detector. And once you make the gas gap, you can put together, and this is what is called RPC. You have the wires, this is called one channel. You read out whenever have any signal. Okay. This is the gas composition we have to use. We have to use this gas composition, and this is the circuit. So you have gas supply, and it goes to RPC, and then goes to the atmosphere in the lab. But if you could talk about ICAL, it is very difficult to waste this gas. So we do the recycling, so we reuse this gas. This is the lab setup. Once you measure and make the setup that what type of detector you want to build in your lab, you go for the industrial production, that means you are ready to produce 2 meter by 2 meter. And this is one of the industry in Chennai which is making this RPC. Now it's at industrial production. We are making 400 of this. How do you know that this gas gap or RPC is working? First thing, you apply high voltage and see it will pick up the current, and this left hand side plot shows you that it is responding your high voltage. You look at the number of parameters, one of them is the timing, it's good enough. You look at the efficiency, is very important. You see our detector is more than 95%, and this is the small scale. And if you talk about ICAL, which is composed of 30,000 of this 2 meter by 2 meter, we don't have that detector yet, but we can do the simulation. And in the simulation, you see that depending on the angle, you see the efficiency varies, but mostly it is more than 95% for mu1. And as I mentioned that we have the capability to measure the charge, and the right hand side plot shows the charge identification, which is more than 97%. Times we can tell whether it's a mu plus or mu minus. With this, we move to the other one, which I said is a hadron. It's very tough because we are not designed to measure the energy. What we see actually, it gives the blob of cluster of hits actually. And we can we use this hit to measure the energy of hadron? Yes. You look at the hit and see that how the true hit looks like is a simulation, and if you have a noise, how it looks like. And you can parameterize the number of hit you get in the detector as a function of incident charge particles momentum or energy. And from there, you do the calibration, use this calibration to get the real energy of the particle. It's a tough job. This is what we do, and you see x-axis is the energy, y-axis is the number of hit. From hit information we are getting the energy. It is not directly getting the energy like in Hadron Collider. So what do you do? Is it so simple? No. You can further analyze the heat distribution and look at the shape of the distribution, and then you get the more improvement using your advanced algorithm, and it shows you how it looks like. It's improved. So we are working hard on getting better and better energy resolution, reconstruction energy through the improved algorithm. Conclusion: neutrino detection is challenging if the source is nature, because source does not change the number of neutrinos produced today and tomorrow is constant. You are in the God's hand actually. If you use accelerator, you can control the production rate. So we are using atmospheric neutrino. All R&Ds have been done in India. This is made in India. ICAL is ready for production. Last 15 years of hard work on R&D now is fully complete, and we are in the production stage. We are ready to do the even 30,000. INO experiment is designed to make a good impact in this field of research. As mentioned, this is the only detector having the capability to differentiate muon and anti-muon, that is neutrino and anti-neutrino. Good opportunity for students to pursue research as a career also, because it is a mega science project, and that will open up next 50 years of research. So this research will put India in global map, and we hope that we get the success in this research. Thank you.
Thank you, Professor Behra. So our next speaker is Professor Indumati. I would like to welcome next speaker, Dr. Indumati. She is working in the Institute of Mathematical Science, Chennai. She joined the Arishchandra Research Institute in Allahabad as a faculty member before she is moving back to IMSc. Her main interests are in physics, particle physics, phenomenology. She is greatly interested in science popularization, and she is editor of a children's science magazine called Jantar Mantar, aimed at high school students. Please welcome.
Indu, IND. Yeah, yeah. Control L change. Oh, Windows. It's not projecting. Okay. Sorry, open with acro read. Right click change. Open with acro read. Open with open with acro Adobe Reader. Good morning. I'd like to thank the organizers for giving me this opportunity to talk about the project. This is a small aside before the next speaker continues on the details of the ICAL detector. So as the session convener has discussed, there are two things simultaneously that we are talking about in this project. One is the INO lab, the India-based Neutrino Observatory lab, and the other is the ICAL detector that we are going to place in this lab. And the ICAL detector will be the largest but not the only detector that we plan to build in this lab. So what I will talk about actually is, as you can see, building the underground science lab. I don't think my pointer will reach over there, so I think you... Huh? No, it's okay. So we'll just have to go by whatever. Yeah. So this talk will be focused only on the lab and its construction. The lab and its construction, due to the very unique nature of this project, a neutrino lab is not just like any other lab that you will build. Many labs exist in the city itself and in India, but this is a little different lab. It's going to be an underground lab, so it involves not just physicists but also engineers, geologists, many other experts. So we have put together this project with the help of many people. So the technical documents that we have used to put this together, first of course the science goals by the INO collaboration, a whole list of FAQs about the project and its scientific goals are available on the INO website. So those who are interested, I urge you to read it. The environmental impact assessment, we are going underground. This is the mountain that you have seen again and again in practically all our talks. We want to build the lab under this mountain, and we know that in India at least, with all our global warming and all our population pressure, mountains are the last places where we have good forest cover. So our challenge really was to find a site where we have minimal environmental impact, and that was helped by not only just the Salim Ali Center, which did the official study for us, but many environmentalists and environmental scientists have helped us to locate a site and given us input as to how we should actually build this project. So that is the second input into our choice or selection of the site. And the third, of course, is the engineering part of the site, and the entire detailed project report, because this project is going to come up in Tamil Nadu, was done by the Tamil Nadu Electricity Board, and they have a tremendous expertise in tunnel construction, and they have done the official DPR for us. So I acknowledge and thank their inputs. And based on these people and the geologists from the Geological Survey of India, I will actually give you the content of how we chose to build the detector, to build the lab where we wish to build the lab. So what is this INO project? This INO project has been approved in principle by the Planning Commission as a mega science project. It will be jointly funded by the Department of Atomic Energy and Department of Science and Technology, and we wish to build it. I don't know, I mean, I'm not attached to this place. I think I would rather be here.
Still you cannot see the pointer. Okay. So we wish to build it here. This is Teni district. We are somewhere at the top of the map here on the right hand side. That's where we currently are. So this is Kerala, this is Tamil Nadu, so it is very close to the Kerala-Tamil Nadu border, very close to Bodhi-Nayakanur, if you know where that is. And so the site was chosen because of, as I said, these various considerations. And this lab will host the main ICAL detector. And I want to say at the outset, because there has been some lot of controversy in the press about this, that it has no strategic or defense applications. It is a science lab. Its operation involves no radioactive release, no toxic emissions. It is a pure science lab whose main goal is to do research in neutrino physics. Associated with this lab, we propose to have an R&D center in the nearby big town of Madurai called the High Energy Physics Center Nodal Center, and various statutory clearances have been obtained. As Prafulla said, we are ready to start this project. So one thing we are very proud of for the first time in India, that we have built a project involving people from various blue dots around India. You can see it practically spans all of India, from A, American College, not quite to Z, but to VCC in Calcutta. So we have many collaborators from many research institutions and universities. It's an open project. We welcome people with interest to join this project. And right now the host institute is Tata Institute of Fundamental Research in Bombay. So I will start now with the main content of this. Why is this lab different? Why is it that it involves so many different agencies? The main thing is that we need to build this detector underground. So why do we need to build it underground? The reason is because of the kind of physics we want to do. Most neutrino labs are underground, and the main reason is that if you look at the left-hand side, we have talked about cosmic rays. Cosmic rays are an open problem in research. We don't know where they come from, but they continually bombard the Earth, and while bombarding the Earth, they produce pions and later muons, and then the muon neutrinos, which is what we will detect in the lab. But before they produce muon neutrinos, they produce these particles called muons, and muons are extremely penetrating particles. And they are not, we always talk about ground, right? Everything is earthed by the ground. So we are not worried when some electrical short circuit, and if it's grounded well, then we are not worried about getting a shock. That is with respect to electrons. But the much heavier muons are very penetrating, and you will find that the muons coming from these cosmic rays can penetrate down to 1 or even 2 kilometers underground, and we have to shield our detector, our neutrino detector, against these background muons. This is the reason most neutrino, or practically all neutrino experiments are underground. And to give you an order of magnitude, even if we go in the, you can see where we have written over there, INO at board. I'm very sorry I can't use the pointer. Professor Kajita, who got the Nobel Prize last year, he works in the lab called Kamioka, which you can see. A little bit below that is INO at Bodhi, the proposed INO lab, a little bit deeper, and you can see that compared to the surface, which is a little more than few parts 10 power 6 muon intensity, when you go about 1,000 meters underground, you will have 3 orders of magnitude smaller cosmic ray muon background, which still means that we have something like 3,000 muon events per hour we will have at this detector, 3,000 per hour. And what is the interaction rate of neutrinos? We expect to see 3 neutrino events per day. So this is the signal versus background that we are fighting against. This is why we need to have really superlative detector electronics that Prafulla just talked about. But most importantly, this is the reason we need to go underground. And as I said, we are forced to go underground because of this one aspect, that we are not able to otherwise manage the cosmic ray muon background. So once we accept that we have to go underground, the primary criteria are safety, because you want to go underground, we will be underground, our students, technicians will be underground. You want long-term safety of the lab, which means you need to find a site which has good rock quality and minimal environmental impact. So this combination is very hard to find, and we found from the geologists that the charnockite, very solid charnockite rock, which is mostly found below 13 degree north latitude in India. So if you draw a line between Chennai and Bangalore, the rock quality south of that is very good quality, and that charnockite rock, in fact the particular rock that we found, the mountain in Bodhi, is a monolithic charnockite rock. We believe will be extremely stable and very good appropriate for building our cavern over there. In addition, because we are on the eastern side of the mountains from Kerala, It's a very low rainfall, low humidity area, and that is very good for the working of the RPC detectors. So we searched around in Tamil Nadu. We found actually a few sites, but we zeroed in on this Bodhi Pottipuram site in Bodhi West Hills as the one having the minimum ecological impact. And you can see from the summary over here that I'll read only the last sentence, that noting that wildlife is rarely reported in the portal area, the impact of activities on them will be effectively negligible. This is the statement of the Salim Ali report. We also plan, in addition, to adopt best practices with active environmental monitoring all through the construction phase. I have a little more to say about this a little bit later. So this is where we are. I don't want to spend too much time on it because I can't highlight anything. The red line going northwest, the bottom right is where the portal entrance will be to the tunnel, and the top left is where the cavern will be underground, and this is the schematic of the tunnel. So what is it that we are going to have? As the mountain rises on the west, we have a horizontal tunnel going into the mountain. So we plan to build a horizontal mountain because, as Prafulla said, we have to build a detector which contains 50,000 tons, which means 50 million kilos of iron. And you can't do that by taking it down a mine shaft. It's just too massive. So you want a drive-in, drive-out tunnel where you can load and unload these things very easily. And at the end of the tunnel will be this cavern, and inside the cavern complex will be contained all these detectors. And you can see that the overburden is all solid charnockite rock, which we believe will be extremely stable. So this is the cavern complex. The largest cavern will house the ICAL detector, but there will be additional caverns which can do smaller experiments, and there are multiple connections between all these caverns for safety. So how are we going to manage the environmental impact? First thing, choice of site, I just, miscellaneous point actually. INO site is in seismic zone 2. This is the lowest zone in India. There is no seismic zone 1. This is the lowest in India, so we believe that it's a very stable terrain. Now, how are we going to build the access tunnel and the cavern? We're going to do something called controlled blasting. In controlled blasting, you have a blast which is done 2 to 3 times a day. In the initial stages, only 2 times during daylight hours. Then when you go further in and the impact is very low, you might do 3 pulls a day. Each blast lasts only a few seconds. This is in contrast to conventional quarries where you're doing continuous blasting, the very well understood process of tunneling. And on the right hand side, I'm not sure you can see the labels, but the very exponentially falling curve shows the vibrations as a function of distance. And within about few hundred meters away from the blast site where you're constructing the tunnel, the vibration is going to be less than 1 millimeter, which is roughly the vibration you feel when a truck goes past outside your house. So that means that when you're about a kilometer away, you're not going to feel the impact of this at all, the vibrations or the noise. And so you believe that there will be negligible impact or near, because the closest village is about 2.5 to 3 kilometers away. You don't want to disturb anybody in the vicinity because there will be at least 4 years of construction, and during that time we believe that we can actually manage this whole thing. I also want to highlight the fact that after they've constructed all the caverns, this is just another science lab. At that point it becomes very ordinary, very few people going in and out, and so we don't expect that during the operation phase there will be any impact at all on the environment or on the surroundings or on the people over there. So this has been actually raised many times. People are very curious, can you really manage this impact of tunneling? So I wanted to highlight just 3 particular places where this kind of tunneling has been done before. One is actually the place which has given us a lot of input, which was constructed by the TNEB, which is the Paikara Ultimate Stage Hydroelectric Power Project in Singara in the Nilgiris. Because those Nilgiris mountains are extremely dense vegetation and forested, they decided to build the entire hydel project underground. It has been functioning now for the last 8 years very nicely, and everything from the water pipes coming in to the tailpipes going out to the cavern to the generators, everything is housed underground. It's a very beautiful project. It has more than 13 kilometers of tunnels under the mountains, and there has been absolutely no impact. You can see that right on the top of the mountain on the left is the reservoir. So they have been digging under the reservoir. There has been no impact on the nearby reservoirs, on the dams, on the nearby area, and so it absolutely stands as a testimony to the safety of underground tunneling. Similarly, in fact, the Idukki, I'm talking here in outside Tamil Nadu state, but in Tamil Nadu itself, Idukki and Mullai Periyar are very important for various other considerations, and those tunnels also, which led to the from the reservoir to the powerhouse, were under construction for 3 years after the dam was commissioned, with no problems to the dam. So we know that we can build these tunnels. The metro tunnels also tell you that there is no difficulty, that in India we know we have complete control over underground tunnel construction. So many of these things, because of the unusual nature of the project, we have been involved in public outreach for many years now. Two such examples are given here. We had a very large meeting in July 2010 where we had more than 1,000 local villagers who finally gave the official consent to, as you can see, with the full support of the local community, as the then district collector said, that INO will come up 3 kilometers from the Potipuram Panchayat, and this is an ongoing effort. I think I personally have spoken in every college in that area. Many schools are there. Many of my colleagues have been talking, not only in the districts in and around Theni and Madurai, but also in the adjoining Kerala, Idukki districts. And one very positive outcome that we are very happy about is that many students in colleges that we have talked to have been extremely enthused and have actually moved to science, because Tamil Nadu has a history of doing engineering. I think probably all of India has a habit of doing engineering rather than science. There has been, I think, a resurgence in the interest in science, in physics. In fact, universities have started offering special papers in MSc in particle physics, which never happened before, and it has been a very, very positive outcome of this whole effort. So this is really what I want to talk about. We are building a different kind of lab. We have involved many people who have all been very enthusiastic about the possibility of having such a lab in India itself. We want to project it as a world-class laboratory. We believe that because already so many people from around India, so many research labs are involved, and we believe that it will actually end up as being a very, very, it is in fact already a very immensely ambitious project. It involves cutting-edge science and technology. We expect that from neutrino-physics we may actually branch out into geology and biology as well. And I want to highlight one thing: the unique nature of INO and the many disciplines it involves offers immense opportunities and of course also a challenge. You have to get your engineering, your geology, your environmental science and your physics right. But we hope that INO will serve as a model project both for its science goals and its sensitivity to environmental concerns. In fact, already projects such as LIGO are talking to us, asking us how we have been doing outreach. We have not been uniformly successful. We are still trying, and I think many people are taking pointers from us as to how such large projects should go ahead, and we're very proud that we will also be such a model project when we come up. So I think that there are tremendous prospects in the physics, in the technology spin-offs, in human resource development, which we haven't talked about till now, and this is especially so since the project, as has been mentioned, is completely indigenous, and there will be more about this in the next talk. Thank you very much. Will you put it up?
So before the next talk starts, there is a small movie which will give you some more visual idea of how the lab is going to be constructed. So let me just let me check.
Observatory, which will host the most massive magnetized neutrino detector in the world. It is proposed to be built under the mountains in South India near the city of Madurai. The lab is set in solid Charnockite rock, which makes it safe and stable. Approaching from the side, the entrance to the complex at about 400 meters above mean sea level takes you to a tunnel about 2 kilometers in length. This access tunnel is 7 meters wide and high and allows for two-way traffic. It also allows measures for climate control, power and water lines and drainage 24 hours a day. After a few minutes, you come to the loading area with parking on the side. Immediately adjacent is the experimental hall, which is shown to house the 50 kiloton ion calorimeter detector ICAL. Room is available for future expansion to include more modules of this detector or any other experiment that may be proposed. Continuing along the tunnel and going around the experimental hall at the back, leads you to the control room, which is housed in an adjacent cavern rather smaller than the main experimental hall. Both caverns will be connected by a network of smaller tunnels, about half a dozen in all. These tunnels, 20 to 30 meters long, provide for immediate exit under emergency conditions. The control room will be fully air-conditioned. It will have the data acquisition system and communication system for data transfer, etc. It may also house a small experiment on its own. It is also connected to the main hall for quick access. The detector can be seen from the side. The control room is also directly connected to the main access tunnel, as can be seen here. The main access tunnel serves as both entry and exit to the INO lab. In fact, the main access tunnel is the lifeline to the whole lab. This is the proposed INO lab in Theni district in South Tamil Nadu, a window of opportunity for students and scientists all over our country to learn and to explore the big world of small neutrinos.
Let us thank Professor Indumati for giving a brief insight into INO. So next, let's invite Dr. B. Satyanarayana, last speaker of this session. So I would like to welcome Dr. Satyanarayana on dais. Satyanarayana has been working in TFR since 1983 and is currently working as a scientific officer Edge. He worked on many major experiments, including a series of underground experiments at Kolar Goldfields, D0 experiment at Fermilab, Chicago, and CMS experiments at CERN, Geneva. He is engaged in building a mega science project called ICAR at INO near Madurai. He is a member of Governing Council of Instrument Society of India and Indian Physics Association. He is a senior member of IEEE and he has more than 170 research publications into his credits. Please welcome.
Okay, so by now you all kind of convinced that how important it is to do research in the neutrinos, neutrino physics. You also are convinced that how difficult it is to do research or experiment, detect the neutrinos. Now the question is, how do we go about doing it? And who is going to kind of do this at the forefront of, let us say, the science and technology that we talk about? The tagline of the Indian Science Congress itself is Science and Technology for National Development. So how in some way the building of INO experiment in this country by using completely indigenous technology is something which coincides with the tagline of this very congress that we are going to hold here. I also want to make one observation. Unlike many of the basic science experiments which we do in material science or other fields, necessarily the detectors, when you do the experiments with high energy physics or nuclear physics, the entire process of building the detectors or detecting for detecting any of the particles that you are talking about has to be done indigenously, and it has to be done using materials which are very cheap, because you typically require very, very large number of detector channels. Okay? So with that, when you start about the INO project, as you kind of know, the primary goal of INO project is neutrino physics, but the INO project actually includes construction of the large cavern, underground cavern, and also the associated surface facilities, and the construction of the ICAL detector that you heard about. And what is also more important is setting up the Interinstitutional Center for High Energy Physics. Now, in the process of doing this major project, a successful INO industry and interface has developed because, as I said before, it's a large-scale experimental science activity. Now, it goes without saying that most of the jobs that are done in typically high energy physics is done by students. Then
it is important to also train for human resource development for this country, that we had this INO graduate training program under the umbrella of Homi Bhabha National Institute or HBNI, and we are in the 9th year of its operation this year. Now, starting from the underground tunnel, which is quite huge. In fact, it is probably much bigger than a large metro station that you can talk about, but more importantly, it is built at much higher depth of the order of about 1.5 kilometers. Now, you heard about various technical details of this project, and the entire project has been kind of studied in detail, and a very detailed report has been given by Tamil Nadu Generation and Distribution Company Corporation Limited, or we also call as Tamil Nadu Electricity Board, right? And this is with their help that we are able to conceive such a big underground tunnel and how to go about building it. Now, as you also heard about this gigantic detector, which weighs about 50,000 tons, but again requires a large collaboration between the research institutes and the industry. And what is shown on this slide on the right side, you can kind of see that the Tata Consultancy engineer, along with a large number of industries, local industries, who are experts in machining, fabrication and structural engineering, is involved with this. If you look at this detector itself, it consists of large number of iron plates, as you see on the right side, which are about each being about 4 tons, about 4 meter by 2 meter in dimension. And also on the left, you can actually see there are several other very large mechanical components. One that you see on either side of this blue path is what is a kind of a trolley which is used for servicing the detector. Just to give you a perspective, you can see the how big this gigantic detector is, about height of about 4-storied building, right? Now, as I said, now I would like to also go a little bit into each of these components that I talked about. The first thing that comes is we are going to build this detector using iron plates. Iron plates come with such kind of a large sheets, each weighing about 4 tons. And we are thankful there is a large presence of steel industry in this country, SR Steel, the Steel Authority of India Limited, Jindal Steel, and other industries who are main partners into building, providing a very high quality so-called low carbon steel. This is a special steel that requires, which will enable us to kind of magnetize this entire detector to about 1.5 Tesla. So we have this capability of producing such steel locally, and once you have these steel plates, you also have to magnetize because you want to distinguish the charges of muons. And then the magnetic coil, of course, is important because we don't have that kind of expertise to produce this so-called oil oxygen-free copper. But all the entire engineering, if you look at it, how you braze these copper coils, how you bend with a large, each one is something like about 15 or 16 meters long. Now, all these technologies, again, we are able to garner support, and we are able to catalyze the local industry to do this job for us. And when the detector completely comes up, the magnet part of it, the coil part of it, is what is shown on the lower right corner, right? Now, I also mentioned about this very large 15-meter tall kind of trolley, which is able to move in and around the detector, but at the precision of few millimeters, is what is shown in a picture on the left side, but it is now a reality thanks to a large number of industries, which are, some of them are based in Vellore and Coimbatore and so on, and the basic design actually is again done by Tata Consultancy Engineers. Every aspect of this goes by conceiving the design, the need by the collaboration group, and we approach an industry and we work not like as if you order a component to an industry, but we are actually equal partners there. Just to spare you with numbers what ICAL is made of, you can really look at it, some of those numbers that are already shown before and some are shown here. Even if you forget about the rest of the whole thing, you're talking about the large number of resistive plate detectors. These are the basic detector elements that ICAL is going to made of, the active detectors. You are going to kind of use about 30,000 of them, which will cover something like 16 soccer fields. It's about 100,000 square meters. And if you talk about reading this data from the detectors, you require almost about 4 million detector channels, right? Compare this with a typical ECG machine, which will actually host about 10 to 12 channels. So these are some of the challenges that we need to kind of meet before the neutrinos could be kind of detected and the rest of the physics can be done. Just to give you one couple of lines about the basic detector itself is very simple. It's made of 2 parallel glass plates or backlight plates and filled with gas of special mixture. There are, if you see on the top and bottom, there are the so-called pickup panels which are going to pick up very tiny signals whenever a charged particle basically passes through. So each of these components, again, as I said, has to be built from very, very low cost materials, and then they are going to be mass produced in the industry, right? This is very important. Now, if you are still not convinced what this project is about, what this detector building is about, look at this table which lists all the RPC detectors that are being employed in this world right now from the top to bottom. If you look at the just the third column, that kind of tells, second column, that tells you what is the typical area of these detectors that are actually used in many major projects. So look at the last column. It tells you that you are talking about 100,000 meters square of RPC deployment area, which even if is much larger than the sum total of all those detectors. And all these have to be built from very inexpensive materials, and it has to be more importantly built in this country. You can't just import like a component that you typically do it in other cases. So you start from, because the basic electrode material is glass, so you have to approach glass industries. On the left you can see two major glass industries. We work with them in tandem to kind of bring a very special glass that is required to build this kind of detectors. Not special in terms of the construction, but you require a very, very large area. Then one of the challenges that comes to apply a field across these plates is so-called, you apply on across kind of paint that is painted on either side of the RPC gas gap. So you have to build a technique. You can't obviously do like by hand the way you do a car painting, etc. And see on the left there is a machine, automated machine, which is built in order to do this. Now you approach a car painting company, because those are people who will have expertise on this. And you can see on the right the entire system, including the control system, that was developed by Walchand Industries and a company, car coating company, on the right side. Then, but when you talk about, it's not just about only looking at one technique. We also look at painting, not just because of spray, also using what is more well-proven technique called screen printing. You see four quadrants, four pictures of how typically the screen printing is done in the case of glass. This is done industrially in a company called Saint Gobain, which is very close to Chennai, located in a place called Sri Perumbudur. Okay? All these processes, the entire optimization of how exactly you want to do, what are the parameters that you get about, is actually done with a very close interaction with us. The way we do it is actually our people being there and train the industry, and then, then they proceed further. Now that's not enough. If you want to place 2 meter by 2 meter glasses along, then you require some kind of a spacers between them, but who will give you very precise spacers, of 2 millimeters. They are not produced, so you have to actually conceive, design, approach a plastic company who will do extrusions or molding kind of thing, and produce those components what are kind of shown on the left. Now please keep reading those company names that are given there. So you will typically see that we already are in collaboration with more than 100 companies to do work for us, and we work for them, and vice versa. So that is the kind of interface that we are talking about. When you want to build 30,000 of glasses, typically, students cannot kind of build this. So you have to build robots who will actually do these things rather automatically. You see one such robot that is shown here, which is built by a company from Coimbatore, which is able to kind of do the entire process of building such kind of RPC detectors. And that is how you will be able to build, let us say, about 30,000 of them in about 2 or 3 years, right? So that is the automatic gas making. Now the signal that is picked up, again, it looks a very simple way to look at, these as a panels which are placed basically a plastic material in the middle and padded on either side by a copper or aluminum panels. But these materials never exist in these industries. So you have to convince them, you have to train them, you have to design them and get them produced in a large number. You require something like 250,000 meters square of these pickup panels. So this cannot be just done or ordered the way you do a typical, let us say, scientific equipment, right? And look at all these industries that are listed on this plot, right, on the view graph here. And as it was mentioned, these RPC detectors use a very special mixture of gas. Again, these are not off-the-shelf components. You can't go and say, please give me a gas system to be used in iCal detectors. So you have to actually start designing the system. And because the gas that you use is very expensive, you don't want to let the gas go into the atmosphere. Of course, it's also a cause concern, right? So therefore, you have to, starting from a very simple system that you see on the left side, you go and build a very, very sophisticated system which picks up the gas which is coming out of the RPC detector and flows back into the loop. So therefore, there is no chance of gas getting released into the atmosphere at all. And you see the kind of volume of gas that each of these detectors will hold. That is something like 200,000 liters square of gas at any given point of time. So you have to handle carefully those developments, right? And now for holding the RPC detectors, you require a kind of special tray. That is also something which you have to build using either a fiberglass or you have to use a carbon film laminated. This is again an industry based in Pune with whose help we are able to build and mass produce these trays. Okay. When it comes to electronics, the information that you want, as it was shown by earlier speaker, is how the particles actually go and track through the detector, right? And also you want to precisely measure the timing of these particles passing through to a level of about 200 picoseconds. You see on the left side a large number of detector functional modules that needs to be built. This is a big challenge because for electronics engineers, when you want to talk about building about 4 million detector channels, we don't even go and buy components or ICs, integrated circuits in the market, because those ICs or integrated circuits or ASICs are not available for your application. You don't find an IC which will work at 200 picosecond time resolution. So you end up actually building these chips by yourself and produce them by yourself. You know, there are foundries, unfortunately not so many in the country, but you go out and actually produce them, but the entire design, characterization, everything is done. You see on the left, they are produced by the Bharat Electronics Limited called hybrid microcircuits, and in the middle you have what is called application specific integrated circuits. This is a very, very challenging area for engineers particularly to design such kind of state-of-the-art kind of chips. On the right you see these timing devices which measure the relativistic particles passing through the detector at a resolution of about 200 picoseconds. These are all designed and produced by us, by the collaboration. And of course, all of these ICs, integrated circuits, have large applications outside this experiment. So that is the big spin-off that you actually see these things. Now what about boards? You require something like 600,000 types of boards that will read the signal from this detector. Okay, just imagine how many boards you would have seen in a PC, in your cell phone, or all your labs put together. Who will build all this? The students, the engineers design these boards. They are of course manufactured outside. Look at this number of companies that we are engaged with, and these really pushed the technology limits of manufacturing technologies, right? Now, just coming on to the other flip side, as I said, I mentioned that most of the work is done by students. Okay, now how do we take the students? Of course, we go through a national entrance exam that is done by TIFR, and based on the score of the students, we actually call students for an interview, and we pick them up and give them a training in the experimental areas for about a year, followed by doing a research program next 4 or 5 years with their thesis, guide, and so on. This is how the PhD program, INO graduate training program works. As I told you, it's already in the 9th year of its operation, and the program started in 2008, and main emphasis, as I said, is on the experimental techniques and detector and instrumentation development. Of course, scientific human resource development for future nuclear and high energy physics detectors is the main idea of why we have such kind of programs. On the right, you can actually see roughly the kind of syllabus or the curriculum that we kind of have. We already have trained, and there are about more than 30 students who have been trained. Some of them have already obtained their PhD, and they are doing very well already in various international labs. And they have extensive and very, very specially designed outreach programs and experiments, not only for PhD students, but a lot of other students come and get trained in our institute. Okay, helping the institutes to set up high energy physics, detector and instrumentation courses is also one of our main ideas of the scientific program. So with that, I come to the summary. I want to say the INO project, with all its unprecedented scale and reach, has succeeded in fostering technologies between, partnership between local industry and research community, and it is providing, of course, Indian students with a training and ground for their skills development in modern experimental physics. Therefore, the local industries and the students are not just the beneficiaries of this project, but we consider them as actual equal partners or the stakeholders. So the project has already started creating an ecosystem of a mega science laboratory anywhere comparable to anywhere in the world, that the local industries and students can only now leverage on and then grow. So as I said, the tagline of ISE, the tagline of INO, I think turns out to be the same: science and technology for national development. Thank you very much.
Please stay on stage. So please stay on stage. I would like to invite the earlier speakers to come on stage, and if people have any questions, they can answer them.
So this is a whole gentleman, which is very kindly, he has said that all these can be incorporated into the structure.
I would also like to just show this slide once. This slide. put this points in front of you as a summary. So I hope you have got some idea why neutrino physics tackles many fundamental physics issues. It's one of the most active and growing areas of research worldwide. INO is a completely made in India science mega project. It's led and implemented by Indian scientists, engineers, industry, and most importantly students. ICAN is the largest detector in the world that can distinguish between neutrinos and antineutrinos, and is best suited not only for the point of neutrino mass ordering, but also has many other possibilities. The infrastructure that INO will create of a background-free underground laboratories and this high-energy physics center for instrumentation development will have an impact which is far greater than the impact simply of the ICAN experiment. And therefore, I must insist that the need for a very timely start to the project is very crucial for its full impact potential to be realized. This is a major project. We have competition worldwide, and if we want to beat the world, it is very important that we start the project on time and take it to its rightful conclusion. So if you have any questions, please. Can you give a mic to? Yeah.
Can I go first?
Yeah.
Sir, my question is for Mr. Satyanarayana Garu. I'm currently studying the BSc final year physics. I'm particularly interested in experimenting in particle physics. So, what are the research opportunities I have got in TIFR? Could you
Yeah, I
please
think,
throw some light on that?
Yeah, I have mic. Sorry, first, so you said what? You are doing your PhD or you?
No, I'm studying final year of BSc.
Final year of BSc?
BSc.
Okay. So this is the right breed of people to come to our labs, okay, and come and discover what is in store for you, and you really see the complete spectrum of what makes a wonderful PhD, okay. The physics, the detector development, the instrumentation, the simulations that you do, what was actually shown. So every aspect of this is in a way is on display, is in a way that we are actually looking for such kind of people to come and get involved with that. And I'm sure within first month or two, you will actually be so impressed and so excited to come and join such projects. I also mentioned to you what is the typical way that we take students as research scholars, okay, which is through a national entrance exam of TIFR, and then you will have an interview and so on. I'm sure with a good background of particle physics and nuclear physics, with a great interest to kind of do the best science that you can ever think of, these all doors are open for people like you. So what is first important is go on the website, have a look at it, what these areas that we work on, and then you contact any one of us. We will be more than happy to receive you at one of the labs. As I think a slide that's shown, we have labs really spread over length and breadth of this country. I'm sure you make a call, we all will be very happy to come and receive you at our lab. And then, as I said, I'm sure you will decide to kind of stick on and do the wonderful science. That is all we people have talked about today.
Thank you very much,
Yeah.
sir.
Yeah.
Thank you for the wonderful presentation. Myself Vishnu, I'm a technician in BRC Kalpakam. And my question is, it is mentioned that ICAL can detect anti-neutrinos. Is anti-neutrino and neutrino annihilation possible? And if so, what is is it form photons like pro-positron electron annihilation?
Hello. Yes, anti-neutrino annihilation neutrino-anti-neutrino annihilation is possible, and in fact, one of the ways we learned that there is a third neutrino is by the reverse process, that is electron-positron annihilation into a neutrino-anti-neutrino. But actually observing neutrino-anti-neutrino annihilation is an extremely difficult thing, and as of now it is more of science fiction. But I mean, what was science fiction 50 years ago is now day-to-day reality. So maybe 50 years from now we can actually observe neutrino-anti-neutrino annihilation. You also said, can neutrino-anti-neutrino annihilate into photons? According to the present theory we have, answer is no. But experimentalists are not always constrained by the theorists. They have their own imagination, and people are looking for electromagnetic properties of neutrinos. In particular, they are trying to see if neutrino has a magnetic moment. and so in future we can think of maybe neutrino anti-neutrino annihilation into photons also.
Thank you so much.
Hello, good afternoon, sir. Sir, the project we carried out now, how is it useful for the India to building as a part of energy constraint?
Part of what?
Energy.
Maybe you should repeat your question.
As the project we carried out is has a part of energy part for the India's development, how it contributes?
So you're asking how it contributes to India's energy program?
Yes.
No, this is not related to India's energy program at all. So this is a basic sciences project and its implications are two very different types. So one implication actually Satyanarayana has talked about, that there is a huge amount of cutting edge technology that you are going to develop in India through local industry which you would not otherwise have had. This is the absolute immediate implication of this project. It is huge amount of technology development. In the long term, of course, there are two different types of implications. One is that, as we have said, we didn't have time to talk a lot about the technical aspects of the physics, but all the world over, actually if any of you attended Professor Kajita's talk, he has mentioned that INO is uniquely placed to determine some parameters of neutrino properties. So we will be contributing in a very fundamental way, as Amol said, if we bring up this project on time, because other experiments are also trying to measure these properties, okay? So we will have better understanding of the world around us. After all, we are in this world and we want to understand as also a matter of curiosity about the world around us. The next very futuristic question is about the neutrinos themselves. Can we use these neutrinos as something? Do they have applications and technology? Around 100 years ago when the electron was discovered, what is the use of the electron? Why do you discover it? It had absolutely no use. But today nobody ever will ask what is the use of electrons. All of you have cell phones. I am talking through this mic. You are listening to me through the speakers. No one is going to question that electrons have been harnessed, their properties have been harnessed for application to improve our lifestyle. So that futuristic thing we don't know, it's completely open, what neutrinos can do for us. Particularly as energy program, no, I don't see that there is any application in energy. But in technology and other implications, I think there is a huge implication for this project.
In case of technology, what implications, main implications?
The whole talk was about that, right? In electronics, in this thing, the types of materials that you're building, there is, the whole talk actually highlighted it. Maybe
the Indian industry is now being able to handle materials, technologies and electronics that it had not thought of handling before, simply because there was no need for this. Because we need this to be done, we give more challenges to Indian industry, and the industry has come true to it. They have actually managed to make the chips, the electronics and the materials that we wanted it to do. This is the
I will make one last point as an analogy. This is not true so far, but as an analogy. You've all heard of X-ray machines, right?
Yes.
X-rays came from understanding radioactivity exactly about 120 years ago, right? Then it progressed. The kinds of machines that you have now, PET scans, MRIs, CT scans, all these are actually at some point they were particle physics detectors. So particle physics detectors have found huge application in medical imaging, right? So whether RPCs will find that application, I don't know. Are we looking at it? No. But the moment industry learns to make these things, I think we are very smart people. I think they will find applications. They will be able to put it to very good use for the well-being of society. So I can only give you a very generic answer.
Okay, thank you, madam.
Yes.
Sir, in our area, there was a major earthquake. So much before the earthquake, there were zoological symptoms. Animals, birds and fishes were disturbed. So whether some type of neutrino is coming from within the earth, it could be an application of neutrino physics. So whether any neutrino is found to interact with zoological species.
Yeah. So,
Me- to answer one, it is indeed true that Earth indeed emits a large number of neutrinos, and over the past 10 years an effort is being made to detect these neutrinos, and the hope is eventually we can use these neutrinos to study the internal structure of Earth. And to partly to answer the previous question, the one you posed, one possible development of neutrino technology is to study the interior of Earth directly. Right now it is done by looking at the seismology and by building models, but neutrinos can penetrate deep inside Earth, so in that sense one can study what is happening inside the Earth more directly. If you ask whether studying neutrinos can be used to predict earthquakes, I mean, my answer would be no, because it is true that earthquakes occur over sizes of the order of maybe 100 kilometers or so, but the amount of neutrinos coming from such an area would be quite small. So I would say that you cannot use neutrinos to study earthquakes or predict earthquakes, but you can use neutrinos to study the internal structure of Earth.
well, I am Dr. Vidyarthi Nanduri. I have worked on vacuum arcs, plasma discharge devices. We use low pressure, high pressure, and I'm an inventor. At that time, right from BHEL, we were looking at TIFR, VARC, at the collaboration between VARC and BHEL, MHD program. Then I am an inventor. I have given the patents to BHEL, and I have not joined Bharat Electronics in the vacuum circuit breaker research. That was with Sherwin Siemens collaboration. There are a lot of areas which you can extend it if you go to low pressure devices development. Last 40 years, there is a lot of groups are working and data are available. It depends upon how you define it. But the whole concept which you are contemplating appears to be very crude. And you can monitor human frequencies, you can also monitor earthquakes, you can also monitor or develop new devices that can be used for industry, fire accidents, or even, even in Australia, there was a lot of forest fires. That also can be prevented if you develop proper devices, and that can be used. So thanks a lot. You are welcome to contact me. You are welcome to contact me. Thank you. We will do that. Thanks for your comments. Yes, here.
Yeah. So congratulations on this mega project. I hope it will lead to Nobel Prize winning results. My question is, you said about the solar produced neutrinos. So they are actually big in number, right?
Yeah.
And is it possible that we can, as you know, ISRO is planning to take satellites to L1 point where there is no atmosphere and all. So is it possible to build a detector which is small in size and detect the neutrinos there? I mean,
Yeah.
you need a bigger detector here on the Earth.
I mean, in principle, it is possible, but the problem with neutrino detection is, as all of us have emphasized, their interaction rate is very small. So we are obliged to build bigger and bigger detectors. So the first solar neutrino experiment, it had 500 tons. That was constructed about 50 years ago. And now we are talking about 50,000 tons, 100 times bigger. So the number of neutrinos we can detect with a detector in space is very small. And the usual reason for going into space is
you can see things there which are blocked by atmosphere, but neutrinos have no such problem. They are coming directly. Okay. So I do not see any advantage in going to space for neutrino detection.
Okay.
Okay, no, nothing of it.
And if I am allowed to ask one more question.
Okay, yeah.
Okay.
you can ask.
Yeah. So about the selecting the detector, actually, you said you are selecting iron, which is low in carbon and all.
Yeah.
But I heard Professor Kajita's talk. I am not from this field actually.
Yeah.
They use it seems water tank.
Water.
So what is the difference?
Okay. The purpose is different, Kamioka and ICAL. ICAL, our purpose is to detect muon and anti-muon, but they do not. They want to just measure the energy, and this is electron neutrino. We are here, the purpose is different. There you can use the material as a interacting. They use water, we use iron. Iron allows us to make it magnetize. That is the distance.
So you can detect both direction.
Yes. That is not magnetized.
Okay. Yeah. Thank you.
So that's the advantage. That's what we can do that Kajita detector cannot do.
Yeah.
Is
Thank
to
you.
detect.
I understand.
I do not see any other questions, but if you have some, you are free to contact all the speakers here after the... We'll talk after this. I think the time is up. So just please, we will talk after this. Sorry. Yeah, because I'm told that the time is going to be up.
Oh, this is the same thing. I think it is covered.
So let me thank all the speakers and here's let me give them mementos from the organizers. So first let me invite my co-convener to give away the mementos. So first to Professor Uma Shankar. Professor Praful Behra. Professor Indupati. And Dr. Satyanarayan. It's my pleasure to present one to my co-convener, Professor Rangappa.
It is my privilege to present a memento to our convener for conducting very beautifully this session.
So thanks a lot. The session is over. We are available here for discussions at any point of time that you like. Thank you. Thanks for being here.
They send signals through internet maybe, or I don't know, some communication network. So